Start recording. Okay, that's running, and the screen sharing is already on. So let's start. I'm a bit sick, so I might sound a bit different and also make some sounds with my nose. So I want to excuse myself for this already up front. So um, I hope it will not be too disturbing. So as said last time, we will this time try to take a look on how we can interact with C++ objects from just plain C. This is something which is quite, I think, interesting. It shows to a large extent how this whole C++ stuff works under the hood. There are, however, some limitations of this approach, so it's not a universal technique, let's say. So we will start a new project. Let's call it C++ hacking. Right. So we have our main file. Let's create some class. Add class. My class. Comment my class. Allow the C in the family. Okay. So we have our class. Let's make everything public. Although that's not so necessary actually. And let's see what we want to add to our class. So I would say what would be useful to have would be a constructor, obviously, so, which for now doesn't do anything. We might add something to it later. A virtual destructor, which also doesn't do anything yet. Then let's add a variable. Eins. And let's add some virtual functions. Virtual void func1 will just printf the class name and the function name. It's complaining because oops, I need to include some headers. So that's that. Root std and strh hash root. Okay, that should be all we need for printf. Let's add the second virtual function 2. Also it's the same. And then let's add this time a non-virtual function to do something which will do something. We call our two func1 and func2. So it's really simple. Func1 and func2. And then measure, let's derive the class. So create a new one. The previous one for my class. Well, we should call this then my base. And the other one will be then my class. My class. Like this. And here we need a constructor again. Calls the other constructor. It's technically done automatically, but here just do it for good measure. We don't need a destructor. Let's maybe add another variable int 2, which we will actually we should set the variable. So let's add here 1 file1 is equals file1. And here we do both 1 and 2. 1 gets assigned by the previous constructor, and 2 gets assigned here. 2 and 2. And then let's copy our virtual functions. Mm, mm, Let us, yeah. So when using virtual functions, once a function in the base class is defined as virtual, you don't need to redefine it as virtual in the child class. It will always remain virtual. And you can use the override keyword to specify that it must override a virtual class. So if you would now comment this class out, you get here a complaint. And the reason for this is that if you would want to override something, and you assume there is a parent class, sorry, a function in the parent class that you're overwriting, but the function isn't there, then you might run into a bug because you are not doing what you expect to do. So you can specify it override so that you know that if this function doesn't exist in the parent, then the compile will fail. And of course, here we will then change the printed string. And I see the typo. Let's fix it very quickly. Okay. So as far as so far so good, this is just a normal C++ class. Doesn't do anything special. So let's first include it in our CP hacking here. So hash my class and that. Let's set my class. My class. 1, 2, 3, 4, 5, 6. Okay, so we've initialized it and just for good measure, let's just do something with it. So we can my class, not sorry, should be small, my class, punct do something, and we will of course print from the subclass the two functions. So we forgot the new lines, so let's add those really quickly as well. You might notice I'm not using the CPP file here. I'm just everything with the header. Is okay. I mean, it's just a short demonstration, so we don't. It won't make the code less readable if we would start moving things here. It would actually make it less readable. So the usage of the CPP file is always also to some extent a trade-off for the readability, or maybe I should say, what is the most readable version, whether to use it or to not, depends on your class. So as you see, and this was working. So now let's comment this out. Create a pointer to this class. My class equals seconds of my class. Okay. We'll just call it P the pointer. That's fine. Okay, now let's create a C++, sorry, a C file. Sure, we could repurpose this since we're not using it. Name. So it will be a C file, and we call it my C class to ensure that we don't run into any ambiguities with regard what this file does. Grab the includes, read them, and the thing is here we cannot include the header. This one because this is a C++ header, so in the context of a C file, it will not do what we want. You can check in properties. It uses the C compiler, but that uses C or C++. It predetermines just on the file extension. So how this is how it works. So to interact with our defined class, we need some things that for our use case will be how to say it, suitable. So something that can be used in C. So type def track underscore as my base. Klammer. As my base. And let's see what's inside. So we can open a side-by-side view. Okay, so we have our constructor, we have a virtual function, we have a member variable, and so on. And the way such an object looks in reality is that first it has a table with function pointers to all the virtual functions in the order as these functions appear here. And then it starts with the member variables. So in this case, in var1. Okay, and for our derived class, we do it very similar. You just need, of course, to have unique names. So I changed the C to an S. And inside, as you remember, since the classes are, since structures can contain other structures, as the base class, we just add this as base. And then this covers this part. And then here we see the only thing that is new is the variable 2. So we add variable 2. And that gives us a structure, or two structures rather, which represent the way our C++ object looks in memory. So now with this at our disposal, we can start think about how to call it. So one thing that would be helpful for us would be to somehow, since this is just a table, it doesn't contain names. So we would want to somehow, in a nice way, be able to access structure, function 1, function 2, and so on. To that, what we do is we create an enum. I mean, you could just type the numbers by hand, but each time, but I find using an enum is more convenient. Index is 0, comma. Let's use a capital E. And then we have func1. And since the enum is automatically incrementing for us, it is really as simple as that. And if we would add here like some in-between function, anywhere here, it wouldn't change anything. So in the when we overwrite, the order also doesn't matter. The order is only the order which then lives in our V table is really specified by how the functions were defined first. So here we could, in principle, for later use, maybe define as a function 3, which obviously cannot be override because it does not exist. So it must be virtual. And one major limitation is that we can only call virtual functions the easy way. We cannot call this to something from a plain C. So if we know that we will have to interact with some class from C only, then we need to take care and have the right precautions and make all the functions virtual such that we will get their addresses later on. In principle, the trick, there are ways how this can work around. So inside the CPP file, we can get the address of, for example, do something and then pass the address to the C file. But this also needs some additional code. So there is no way to, if you are just given a C++ class and can only write C files, there is no easy way how you can access the addresses of the non-virtual functions. So this is one limitation. Of course, if the entire class as such would be in a DLL, then usually all the functions are part of the DLL's export table, which gives us completely different mechanism of resolving the addresses, which then we could use to call it. But here we are in one program. We could, of course, mark those symbols for export, but that would complicate things. So we might do it later. But now, for starters, we will just work with the virtual functions, as this is the well, a straightforward way, so it doesn't require too much workarounds. Okay, so what we would then want is the ability to call those functions that we have here already found out their indices inside this table. So let's create some functions which would allow us to do that. So and this here will be different depending on whether we are using 64-bit or 32 bits. So let's use the preprocessor underscore m underscore x64 l -28 to have two cases and two different implementations. So void func1 s my case const pointer object, and then let's brackets object vtable function1 index that go to be cast. So the right type here is void asterisk oops, bracket const void asterisk. Then the whole thing goes in brackets, and then we call it and pass object as the first argument. You might remember from when we took a look at how this is implemented, this functions on a class, that this object, or in this case we call just object, is passed as the first argument, which for us is not visible, so we call it here without it, but the compiler adds it. And of course, if we do everything manually, then we of course also manually need to add this first argument. And if you would have a function with more arguments, then would you of course have more of them, which we could add later. So I'll just duplicate it, function2, and then just take the index of function2. We copy the whole thing. The 32-bit version is quite similar. We just need to specify the right calling convention here. Underscore is call. Should be it. Okay. So let's create a test where we try to do something. So void my test1 takes a void ptr here as generic as possible. So it takes anything as long as it's a pointer. And now we do some casting. S my class asterisk and my class equals I think this should be an S. I think it should accept it. Yeah. So in C, the casting of pointers is not type sensitive. So while in C++, when you're casting, you can only cast two void without an explicit cast operator, and you can only cast the same pointer types onto each other, implicitly, that is. For different pointer types or incompatible pointer types, you need an explicit cast in C++, while in C, you can cast any pointer to any other pointer implicitly. I think that will throw a warning, at least it should, because that's dangerous. So let's see. No, it didn't. Did we set the warning level high enough? It's being really annoying starting with level 4. And then of course there is the option to yeah, so here well, it's complaining that it's not referenced, and well, it's complaining about those but not about the typecasting. We will see. If it doesn't complain, then it's fine, so we will leave this as is and continue. So one thing we can do here, we could already read the member variable, so we can printf $d, comma $d, backslash comma my class and base variable one, and the other one of course doesn't need the base since it's already on the object. So this gives us the ability to exert those. Let's see if this works. It won't because we need to call it obviously. So here we will see. You can use this extension either in front of every function definition or as a code block. And this way you can add C style function prototypes to a CPP file such that they are then callable. The way the function names are decorated between C and C++ is different, so you need to specify that the function names should be C style and not C++. So, as you see, we could access those member variables, and just to show you what would happen if we forget to extend C. It won't compile, as you see. Oh, well, it won't compile because I missed a slash. But then it won't link because it cannot find this function. And the reason it cannot find it is that it's differently decorated. So it has some, if you get an underscore added before the name, if it's just a C function. So this way it will be fine. And if you want to see what the other naming would look, we can just go here, rename that to something else, and then try compiling. And we see, yeah, so in this case, it has less decoration. So the other one has this underscore C decor and specifications about the arguments it takes, but here it just uses only the name and nothing else. So that much of a difference. Let's run it again just to see that we fixed everything. Okay. And now let's continue. So now the fancy part. Let's call the function func1 von my class, and then func2 von my class. Func2 von my class. Okay, now let's run it again, and we see called the right function, so my class, as expected. Is that clear so far? Okay, no one is saying anything, so I guess it is. Maybe let's quickly add an example where we have an additional argument. So let's add to function 2 some int val and function 2. What's in there? Comma val. So obviously we need to add the same argument here. It's already complaining. And it would be nice to use this here as well. Okay, so in this case, here we would then need to add comma int val. Of course, need to add segment here as well. And here and there. And then we want to use this argument. It's already complaining that one argument is missing. Val, comma, val. And voila. Oh, no, almost. Here we need to use as well. So let's say, okay, let's run it. Yeah, something's not right. Here, we need of course then to provide something as well. And voila, you see it works. So the more arguments we have, just the more arguments we need to add to this definitions here, and it works fine. Okay, so next thing we'll try will be to create such an object, which could then be passed to something that expects a C++ object, and then works with it. So void asterisk, but we want to be type agnostic, right? Okay, so copy a bit. Class my class. Okay, then let's look size of is my class. Okay, good. We could now have a check. If this is null, then we return null. This is null, then we return null, just to have this code be fail-safe. Maybe we don't expect malloc to fail on more than this, but it could essentially. So better to be safe than sorry. Okay, so base vtable, and now we need a vtable. We don't have one. Technically, there is one which exists somewhere, but we don't know its address. So if we don't know its address, the next best thing what we could do is we could just build our own vtable. That is reasonably easy. So let's do it here. Find my class vtable equals should be correct. Point. That should be fine as soon as we add something into it. Void asterisk and void asterisk with the right function pointers here is nothing, no content name. As my class underscore struct, and we copy this. And the names here, those functions here are missing, so we need to add them as well. One, punct2. This one will need an argument, but at this level we don't care. So now let's just copy. Let's start with the first one. Void destructor const void string object. Destructor here will not do anything in the same way as the real one. Now we have func1, which will printf text my mouse func1 and this /n. Oops. Okay, now the same for func2. Just that we need to not forget to add the other argument. Though if we would forget, it would just ignore it. So it wouldn't be the end of the world. It's not offense not send there. Okay. So we have our vtable, so we can now assign a vtable. As you see, all the instances, no matter how many we create, share one shared vtable. And for C++, it's for the normal C++, it's the exact same thing. We have one vtable which is shared by all the instances of all the classes. So each of the classes only have one pointer. So this is really quite memory conserving, so to say. It doesn't need a lot of memory, no matter how many functions you have. Okay, so we need to set the variables. So first let's set the base variables. Let's say we set it to 111 and 222. And last thing is of course to return our newly created object. Okay, good. So we go back here. We comment out our test. Now we create an object. So let this open one. Copy this part here. Is equals. Right, we need test2 here. Void test2 arguments. Test2. Okay, now can you still hear me, or is there a connection interruption? Seems the connection is broken. One moment, please. I think I was gone for a second. Right, we need to cast this, as I said. Sec. Okay, and now we can, in principle, even call do something here in our C part, because do something will then look up the function addresses from our vtable and call them. But instead of calling the do somethings on the real class, it will call them on our self-made mockup class. One thing that of course here is also missing is the destructor. So oops, let's see. Right, like test2, my test2. Like this was the right name. Test2, sec. And as you see, it called correctly our internal fake functions. So it works as expected. We can create an object which, as long as which allows us to override the virtual functions with our own, and this is already quite nice. So if we would want to manipulate something, we could, for example, create such an own object where the virtual functions do something else, and then just make the original, and then just pass this fake object to some library that will then internally do something with it. And if we got all the variables and all the virtual functions correct, then it will work as it should. What we also could, of course, do is we could create one of those objects and then get its vtable address and then use this instead. It would simplify things, but of course our goal is to override something. So the next thing we will try will be, we will try to create an object as before, but instead we will want to redirect some of its function calls. So let's comment this. Make here again a test3. Test3, which takes a pointer. Now we'll create of course our test3. Okay. Right, so let's see what we need for test three. Um, so first thing we'll need will be a new vtable, something which can replace the old vtable. So right, asterisk new vtable equals dialog size of right asterisk size of right asterisk times 3. This is how many functions we know there will be. Now, and then we copy. Let's use the S version, otherwise it will complain. What's the crazy all capitals. Pretty sure I just use non. Maybe it will complain. We are missing an include. Let's add Windows HTML function. I think the save things are not defined in the SDIO. Yeah, mems QIS. Okay, so destination is our new table. The source will be just not upfront string, comma, to the same size already had. Okay, so at this point we've just replicated the vtable. The way this implementation will this is something. So destination size. That is a bit of different syntax. Destination size, comma, source. I will get a comma source and source size, and they are the same size. So let's do this. Okay. And as I wanted to say before, this implementation is creating a bit of a memory leak because each time we call it, it creates a new vtable which we are not tracking. So if you would want to use this technology in some real project, then you should like initialize the vtable once and then just keep it around, maybe with a static variable or something, depending on your preferences. Okay, but anyway, so let's now the last step before we do the intermediate steps. Replace the vtable of our object with our new vtable. So at this point, it's just a copy, so it will behave the same way. Missing an asterisk here. Okay. We can quickly check that it's still doing what it was supposed to do. It's calling the my class function 1 and 2. This is fine. Okay, so let's now hack it. So it says next one is equals, and we need of course a hacked function for that. We can copy those two. We could use them directly, but let's oops, didn't copy properly. Right. It's like Okay. And this is the function 1. The other one will be the function 2. Fine. And let's run it. And voila. Instead of calling the right functions, it called our hacked functions. Good. And what we also could do is can do it in a once more extreme way. So here we needed the pointer, but for the next one we'll still need it. Test 4. Test 4. But test 4 will be much more extreme because this can go up. This can be commented out. We will create a new object, completely new object. My class 2. That's not here. And then we will on this new object call do something, and it will still call our hacked functions. Let me show you how this will work. So we have our hacked functions which we will use. We need a new function here. Okay, so what we want for the vtable, so void asterisk asterisk vtable is equals asterisk void asterisk asterisk ptr. That's the pointer to the vtable, which as mentioned is shared amongst all objects, including those which are to be created in future. And now the straightforward thing would be just table at, let's say, function 1. It's just equals hacked function. That will crash because of memory protection. You can quickly experience it. So here we get a right access violation because the vtable is in a read-only part of the memory, or rather a part of the memory which is marked read-only. Since physically all the memory in your RAM is read-write, so what we can do is we can use a Windows API function to change the page protection on this memory region so that we can edit it. So we first create a variable to hold the old presets. Then the address, the table, comma. Then we need its size. While we provide here a size, what effectively happens is that it will protect or unprotect the whole page. So the size is not so critical to be exact. Page. You can just always take something that's bigger than what you expect you will need. Right? This is the unsafe situation. Memory which is executable should not be writable, but we need it, so we do it. And once we're done with our modification, to return at least some resemblance of security, we just return it back to the old value. So the way this function works is it will write into this old variable the current state, then it will do the change. So we can just use it again with old as argument to restore everything. Now when we run it, as you see, function 1 has been successfully hacked. And this, despite the fact we have even created the object after we have applied our hack. So of course here you could use this mechanism to just point the thing to some C++ function. So we need to use a C function as your replacement function. And this also might be useful if you have something where you want to modify the behavior of, to do it this way. The reasons for this would be if the new which is invoked on the object is done somewhere inside the library where you cannot just replace it with a new from a type which you have derived. So instead what you could do is you could use this trick to derive an own make like all the news or the creations of this object use your hacked function instead. So in practice, this is of course a bit complicated because if you would, for example, want not to manipulate all the instances, just a particular instance, then you would need some way to find this out, whether you are in a manipulated instance or not. And another limitation is, of course, that you cannot attach additional data to the object. To create a derived object, then you can, of course, just add additional member variables, and once new is invoked, it will allocate the right amount of extra memory. But if the new is invoked on on another object which is not overwritten, then of course there is no way for you to attach additional data. So what you would do in such a situation, if you would want to make this somehow more useful, you would track the addresses, the memory addresses of your this object, which is passed here as object, and then have, for example, a hash map where you can store additional data based on the address here. And this would allow you, if you also add it to the destructor, the best approach, since the constructor is not virtualizable, so to say, will be to just check whether in your hash table there is already an entry for the current object. And if it is not, then you run some initialization code where you create a new entry in your hash table for this object. And then on subsequent calls for this object, you can you can retrieve the entry. And in the destructor, if it's virtual, you can even clean up the entry so that you don't waste any memory. So are there any questions? Okay, no questions. Then maybe let's take a short 10-minute break. And after the break, we will maybe create an own hash table. Since I mentioned those already a few times, and hash tables are quite useful and not too complicated, unlike binary trees in maintaining. So I think we will have enough time to make our own hash table. So I will turn off the mic and the camera and be back in 10 minutes. And if you come up with any questions in the meantime, you can ask. I'm listening, so I can answer questions at any time.
I wanted to ask, when will the homeworks be graded?
Together with the final project. So at the end of the semester.
I see, because I'm not sure, like, if I use like some of the homeworks, I'm not sure if the method I use is like intended. So that's why I want to know if I did everything correctly or not.
If it's like outrageously bad, I will write you an email and give you the opportunity to fix it.
Okay, so that's the same for the final project, right? So I assume like if there's some problem, I can have the chance to fix them.
If it is like obviously completely wrong, then I will write you an email and give you a week or two, depending on how big the problem is to fix it.
I see. Thank you.
Welcome. Okay, I think the 10 minutes are more or less up, so let's start a new project with our hash table. So we will close this and create a new one. Hash table. Great. Do you have any preferences whether you would prefer to see a C or a C++ hash table?
Maybe C++ hash table.
Okay, then let's create
Yeah,
a
I'm
class.
also for C++.
Header file. In this case, we only need a header file because it will be a template. And my table page. Add. Okay, let's think about it. What we will need. We will need obviously at least two arguments. So template type name. First will be the key. The second will be the value. And what we need for hash table is something to calculate those hashes for us. So we'll add yet another type, H, and we will add a default hasher from K. So default hasher is yet another template object we'll create in a second. And class, table. Wait, how did I do that the last time? Did I put this into a namespace? I think for the array, I put the array into a namespace. TTT, my array. My array H. Yeah, I use this my framework and then my array. So my framework can copy to my table. It's not my table, it's just hash table. Well, okay, then it is. And here we open, and here we open this file and just copy bit code to have some consistency. I want maybe rename that. I named the file fine, so we will leave that as is. We don't need to rename the project. Like my array, so here it will be my table. Want consistency. We don't have anything else for now, so it's consistent. Just like it a bit. Okay, now here let's create this default hasher. So template key. And this will be struct default hasher. And it just has one operator. This is a special type of operator. It's like the, how should I call it, the function operator. It allows us to use the object as a function in a way. Right. Const k reference k key. Const. The thing is const. And what we now basically want to do here inside is we want to somehow calculate 32-bit unsigned number, which when given different instances of the key will give us a as uniform spread of return values as possible. Our performance of the hash table will be contingent on this behaving as expected. There are a few standard methods. We will here implement a simple one for usually for strings, but it should be good for any binary data. So start with an unsigned int hash initialize it to start value. The connection is lagging again. I hope it will be working soon. I just reconnect. Back. Right. So, let's type. No, I was typing 81. Actually, internet connection here is really not great. Sorry about that. But when one travels, one doesn't always get to pick one's internet connection. 5, 2, 8, 1. Okay, now it goes. So we just want a start value which is random enough. We could use anything that is a more or less nice distribution of bits. And now what we want is we will need the size of the key, which we'll just get with size of. So this is quite easy. And we'll just go through every byte in the key and hash them. So for unsigned char asterisk ptr ist gleich unsigned char asterisk. I was cleaning my nose. A coincidence. My remote desktop software should automatically reconnect, but if it tries to do it too early, then it runs into a disconnected situation from which it doesn't recover instantly. Okay, so we need to cast our key appearance A. No, sorry, not K, but key, comma. Now, let's see if we are there. So PTR must be less than this thing. That should be a semicolon. The semicolon, circ r plus size of k and ptr plus plus. We could in principle optimize this code by caching the value with which we are comparing. Okay, let's do that. Just call this end, comma, end. Key, comma, end is equals this. And we have here plus plus. We will iterate through all of them. That's good. That's what we want. So now the only thing to do is to mix the things up a bit. And a common way of doing it is the XOR operation, the exclusive OR. So what we do here is, since we are kind of entering this operation with a with single characters, and the key might be very few characters, and we might the connection of again. Okay, this connection should be a bit more stable now. I changed some my network settings. Okay, so where were we? Hash is equals, and then first of all we shift a portion of us things from star initial value by 5 bytes. Then to this we add, yeah, it's reconnecting almost instantly now. We add again what we have. We are mixing things up really good. And then once we're done with the mixing, we XOR the result which we have created, asterisk PTR, so the next byte from our key. And once we're done, we just return our hash. This is a standard algorithm. It works quite well with most keys. So generally, I would recommend using it. There are some which are, I think, especially optimized for ASCII text and for other things, but if you just want something generic, this is a good approach. So the thing, what it does is, as mentioned, it gives us a key from the key space, which will be then used as an index in our table. So let's see what we need next. So we will need in our table some thing to hold the data. So it's usually called the bucket. So let's create one. Bucket entry. And such a bucket entry usually is a single linked list. What single linked lists are, you already know. So I'll create a bucket from a key and a value const reference key const key reference value, and here we will make a default constructor so we can create of our of our class a bit, because it requires us to only use values for which a constructor exists which doesn't take any arguments. But this usually is the case. So there are only very rare cases where you would have an object which necessarily require you to provide a constructor. And then, of course, we can just work this issue around by storing just a pointer to the object in the table instead of storing the object itself. So this is not that much of an inconvenience. And of course, then we will initialize key of toggle point, key with key, and value with value. Then k key and our value, obviously. Right, I would like to leave value to be the last end, doesn't matter at all, but for the C version, it will be important to have the value last. And here we'll add the hash, initialize equals 0, and the next bucket. So as bucket entry, asterisk, next is equals PTR, semicolon, okay. So this is our bucket, and let's now create some basic constructor and a destructor. Oops. Stack. And let's take a look quickly to our array implementation. We implemented it using copy on write. So we will here also implement the table using copy on write. So let's go now down to the protected part of the table. Okay. It is not great when the connection breaks when you're deleting something because then it thinks the delete key is still pressed. So just undo all that mess. And now the undo key got stuck. Right. That's where we were stuck. Okay. So extract this data. Asterisk MPTR equals PTR. Here we will need volatile ulong fs 0 again. Volatile ulong fs 0. Size 10. Count. How many entries there are? Size t. Oops. Size t bucket count. Also 0. In column. Our buckets, which will create as a array of zeros. Trick I think I already showed you, but it only works for the last element in a structure. The compiler might it's I think if we stay at the one level 3, it will not even warn us. Slash my table. So let's see my table on right. It was my FA, my frame, let's see. My framework. My table. And let's for starters, let's include maybe string. String is nice. So string complicates things. Let's just create a table of two instances for starters, then we can create something more complex. No, my mouse is not working. Please. That is annoying. I had this issue already once with the remote desktop. When it fails too often, the mouse synchronization is I will have to recover that really quickly. Mhm. Mm. Still not working. One moment, please. Um, no? Yeah. Let's see if the recording is still working. Okay, the recording is still working. That is good. And nothing else works again. Where we at my table, int comma int, my table. Okay, and I will quickly compile to see if everything so far doesn't complain too much. We have already added it to be an asterisk. Oh, it needs to be a T. Else. Right, and it's missing. Sure, it's missing those values. Okay. To speed up things, we can grab make exclusive and attach and detach and realloc and alloc and make data. And let's call this just consistency or just my data. There are a few things which are different, so it's not really okay. So we don't have capacity, we have bucket size, bucket count. Don't have data, we have bucket plural. Which we want to call a distractor. We don't need to, the distractor doesn't do any. We know it might do something, so let's keep it. Then we destroy my data. This is fair enough. Just that this should be an error with I think. This buckets is now a pointer, an array of pointers. Destructor, see the whole thing. Right. Yeah. This will be here more convoluted. We don't really have a distractor for that. We need to clean this up manually. So here I'll just comment these out and say to do clean up our buckets. And in principle, we don't need a distractor, but it doesn't have any anything that it would need to distract or could distract on its own. So this we can just comment out. Okay, attached data is fine. Capacity, right? We will have capacity, but bucket size, bucket count. Yeah, that will be very difficult. So let's just comment this out complete. alloc just takes capacity and waves data with capacity, and size of bucket asterisk, or just void asterisk at one decimal point and listed at buckets. Okay. So this one update. And we need to clear the bucket. So name set. Name set. Actually, we should have saved name set. PTR. Buckets, comma null, comma bucket count times size. Right. Good. So we have cleared this. We can see this. We can see this. This is just like that. Good. One thing we already know is that detached data can be just put into the destructor, and we can provide enough function which also just test it. The constructor can stay empty. We don't need to initialize anything up front. Might be, of course, an optimization if we add the ability to pre-allocate some size, but now that should be good enough. And let's add a function which will allow us to add something. So now this will be verified. Insert const key const value. So key value. We could have additional parameters specifying the insertion mode. So like fail on duplicate or allow inserting duplicates or override duplicates, so we can customize the behavior. But for starters, we just will make it very simple. So what we will do is here we will add, just call it internal function for now. So the idea is that the insert value is kind of just the insert multi. So insert and ignore and ignore if another value exists. It just adds another value. And if you want to customize our insert, we would have the checks before. So we'd have first a check that looks up if the other value, if a value of this key already exists, and then it would decide whether to overwrite it or to fail, or whether to allow the insertion in case we are in the insert multi mode. So we needed to have could implement it such that we require already there to be a entry. So we could set insert if nothing exists, then to create something to make exclusive. Yes. So insert will just before it does anything make exclusive with I guess with 0, or we could start with some reasonable size. Let's say we start with 10 entries. To make exclusive 10 entries, and then when we are in insert, so here we know that MPTR already must exist. So let's see. Um, let's see if we have enough buckets already allocated. So if ptr bucket count is greater or equal count bucket. So we check the count is greater or equal bucket count. So count is like the amount of elements, and bucket count is the amount of buckets which hold those elements. And since we want to some extent not have too many buckets which might be empty, we will say that here we will divide this by 2. So we want to have half as much buckets than elements, so that usually we'll have at least 1 element per bucket. In some buckets there will be more than 1, depending on the keys, so that is a bit unpredictable. I mean, it's deterministic, but it's for the user not transparent what will happen. Okay, so in case we have too many elements, then we will resize our buckets. So size, compute a new bucket count, which is then just ptr bucket count, but there is a special case that might be 0. I mean, we initialize it to 10, but if we would initialize it, then initialize it to 0, then might have such a scenario. So if it was 0, then we just want it to the new size to be 1, and else we want the size to be just count divided by 2. That we are consistent here. Okay. Good. And then we record a function trying to create resize buckets, which takes a new bucket count as argument. And if it would return error, then we need to check for the error, but now we don't return error, we just use it as is, so void resize bucket. And while implementing this function, we already learned most of how this works. This thing works. So we need to create new data. So my s what's his name is my data. My data asterisk tr is equals next new. What's the name for it? Alloc. Alloc already attaches, so we will just make data. Make data from bucket count. So here we have a new thing, and then we will create here we will take out all the entries from the old data. So as bucket entry, oh, damn it. As bucket entry asterisk p and is equals pointer. For size t I is equals ptr bucket count, comma I minus minus, comma. Okay, now here inside is bucket entry asterisk reference entry equals ptr bucket count and buckets from E So what we're doing, we are looping on the outer loop for all the buckets, and now we will make an inner loop through all the entries. So P entry is not PTR. Okay, and now whenever we find something, we S entry, okay, separate variable, and the next is equals P entry next, then we make P entry next, correct, P head, for the head, then we make P head entry. We are swapping the elements, and then P entry will be the next we just cached before. So once we are done with the loop, all the entries that existed in the old data will have been transferred to the temporary linked list. And we set bucket count 0 to indicate later we have to do here that there is nothing for us to do because all the things that were there have already been taken out. So we just need to free the whole thing and we will be done. Okay, so now for our new object, we will set the count to PTR count. If we are inserting the elements, then obviously we will need that. Now we can already attach data PTR that will dispose of MPTR. Now it's still empty, so we need to take care of that. Why? It's not now PTR. We'll be adding the things. So this, okay. Now we call another function insert entry, which we'll implement in a second. P head and P equals P next. Okay, and that's as much for the resize bucket. Now let's go to the insert entry. By the way, the insert entry, or maybe before we implement insert entry, let's finish this one. So we have here our resize. We have resized, so then we want to create a new entry. So as bucket entry, then let's go with maybe malloc. Now let's go with malloc. Malloc is more useful in the sense that we can later add a custom allocator as another template parameter. Size of bucket entry, yes. Now we need to call the new bucket entry, new constructor of the thing, the constructor of the thing, I mean. Okay. And the constructor should already take values to take the key and the value. If there is a value, we could improve this. But I think for the simple cases, okay. It takes just the key and the value, so initializes this. Then P entry. We still have to set the hash value. We could set it in its constructor now that I think about it. But let's do it this way: is hash 1k 1 key and okay. Now the entry is pretty much done, so we can use the same not yet completed insert entry function to add it to our existing table. Right, so we are now missing two functions. The hash function. I will start with the hash function because we will need it later as well. So, and it's super trivial. So, long hash. What was it? Const reference k key const hasher one hasher key. Let's go to our insert entry function. So void insert entry entry. Okay. Okay, and now we need a few more helper functions. So first of all, we need to find the index in our array of buckets. So st index is equals map bucket index, which takes entry hash. This is a function which we will create in a second. Hash, okay. And yes, bucket entry asterisk reference equals mptr buckets at index. Okay, talk about bucket by reference, so we can change it. So so pn3 next is equals bucket, and bucket is equals p-entry. So we always add at the top, and all the entries are pushed down. Okay, now we need our map function. So long map bucket index long hash. What we now want to do in this function is to somehow from the size, sorry, from the hash, generate an index which fits into our bucket size. And I noticed there is a small implementation artifact which would not work for us here. We want this to always work in powers of 2. So we will grow and shrink the thing always by a factor of 2, which also means that the initial value of 10 is not good. Where do I initialize the value here? Let's start with 0, then it will default to 1, and then grow it by factors of 2. That is reasonable. We could implement it such that it can work with any size, but it would be more computationally complex. So we will here use a very simple trick. So we just return hash, we use the AND operator and ptr. Oops, what happened here? Hash and ptr. Bucket count -1. And what this effectively does is it will flip all the top bits, highest order bits, here. Sorry, what it will do is we can write it, or we can write an example. So if we have, let's say, 8, what's 8? 8 is 1, 0, 0, 0. 4, 1, 2, 3, 4, 5, 6, 7, 8. 3 zeros. Okay, that's fine. If we have 3 zeros, and then we make this -1, what we get effectively is 0, 1, 1, 1. And this can act as a bit mask. So if we know that this index is not a valid index, it needs to be one less. This way, we can generate from a hash value, which can be arbitrarily large, indices, which will always fall within the valid boundaries of our bucket array. Let's write a comment here. Because this is a very particular implementation. Note this works only with heads which sizes are a power of 2. This can be generalized by using the modular operation instead of the end. So using the modular would be more intensive. So we would want to avoid it if we can. And the thing gives us now an index which will fit. So we have this. I think we have everything. We don't have the lookup, but we have at least all the insert functionality. At this point, it probably would be good to clean up the thing. So resize. Right, so this was our resize function. I will just copy this piece of code here and put it there. Oops. Let's see. We go for all the buckets. We're counting them down. This is fine. And then inside, when we have one of the buckets, we are emptying it. So here, instead of adding it to head, we will just, or instead of doing this either, both, we will just dispose of the things. So entry just S with a typo. Not typo. No, not typo. That should be fine. I just called the destructor on the thing. And since we created the row with new, we also need to free it. Destruct and free. And then we advance our loop to the next entry. Good. We actually need realloc. Now we want need realloc because we always use the other thing. So make exclusive would be here resize buckets to the same size, and alloc is are using an alloc anywhere. We might use alloc, in which case we could simplify it a bit. Yeah, we can just use make data and get rid of alloc entirely. If this thing does not exist. Oh wait, we have a special case we don't think about. As if oops. Also, if ref is more than 1, then we need. Otherwise, we can just use it as it's nothing to do. All is fine. Yes. Yeah, that should be fine. I'm happy with it. adding any sort of more advanced iterator support here would be complicated, so we won't do it simply. Okay. We will just make it like the other array where we say that you cannot make anything that would make it exclusive between using your iterators. Okay, so we have this. Then what we'll then need as next thing will be a function to get something out. So v get just get here from g. Okay. And this thing will also call a internet function void get ptr, and that's right. The asterisk get ptr, get pointer, which takes the key. So the asterisk ptr p value is equals get ptr from key, and if p value, then return asterisk p value, else, oops, else we don't need to write else since return time is anyways, return a new empty v field. And then we of course need to take a look how our internal implementation will look. I mean, I have a bad idea. I'll not call it get ptr, but I will call it find entry. And find entry. And this needs to be an asterisk, obviously. So I find entry. Entry. Now there is a type of it. See. And entry from key. If we find the entry, we can go with entry asterisk value. And this find entry will be useful later on for the remove function as well. Okay. So of course, if there is nothing, so if exclamation mark and ptr is then return. As you might notice, I have not implemented any assignment or copy constructors, but that would be very analogous to what we did for the array. So I won't spend time on that this time. If you want, you can just copy the assign and this tool and this tool, and maybe modify and apply those if you like. I think we won't redo it because it's extremely analogous operations. So there's no value in Okay, so nice, let's go 10. Index is equals map packet index hash key. Okay, and now what we'll do is we'll start there. So for s get entry entry is equals ptr ptr buckets That's next, okay, comma. Now in entry is like PTR, and the entry is equals to entry next. So here we are having a undestructive loop. Data loops usually were destructive in the sense that they have removed the element once they encountered it. So this loop is more simple. Now we will be going through all the entries in the bucket for the index that was generated from the given hash, but this doesn't mean that they all will in fact have the same hash. Since the hash value is truncated, so only as much bits as needed to cover the index range of our bucket array. We now need to check if the entry hash is, I should have kept the hash lowercase. Hash is equals hash. So if this thing is not equals hash, then continue. We just go to the next entry. But if they are the same, then we are checking if the keys match. This is the next catch. You can have keys which are different, but which still give you the same hash value. This usually means that your hash function is not performing well, so you should replace your hash function with something better. But it may happen even with the best hash function. It can happen. It's just a question of statistics. So that is what it is. And if this is true, then we will return entry. Now we don't have here yet a mechanism to address like the second or third occurrence of the same key. As I said, we could have a situation where we would want to allow for multiple insertions. Here, this function does not take care this doesn't take this to account. We could add an argument like to skip, so that here, if it finds a match with a key, it decrements to skip. We should do it. This is not so difficult, and it takes less time than I'm talking. So team to skip is equals null. We won't use it probably, but we just add it here so that one knows how such a thing would work. And if to skip minus minus is equals 0, then we return. Else we just continue to the next. And of course, the different keys might be intermingled, so we can decrement to skip only once we have a key match. And if we manage to exit the loop without the return, then return PTR, because it means that there was no match or a skip was too big. So like if you have like, let's say 10 entries and 3 of them have the same key, and then you are iterating with to skip to the next and next, at some point you will not get the next because you have already stepped through all of them. Good. Okay, we have about half an hour left, so let's implement a test case. So my table point insert to 1111, 1. What is it complaining about? Inaccessible. Didn't I make this public? Insert public should be public. Oh, I have to insert. Second one was supposed to be called insert value. That explains it. So let's add 2, 2, 2, 2, 2. 3. Now let's say we want to get one of them. Int that is equals my table get 2. How many please? 4 2s, 2, 2, 2. So we expect the return value of this to be 2. Let's run it. Oh no. That's the annoying thing about using templates. You get the most of the errors only once you try to run it. What is it saying here? Type mismatch. Const long expression long. Small transposition. Then long. P values. Right. He had that should be a capital H. Seems we have typos and capitalization mistakes, but so many. Make data think is nothing, then you make it with 0. Yes, that make it is reasonable. Right, we exclude the argument more. Okay, and return is failed. Okay, not working quite right. Let's see. Table F1. Okay, it's not working at all. Oh, I think we also forgot to increment the counter here. That will of course be a simple mistake. Counter cross, but that won't be the only one because insert bucket. Oh, index is completely wrong. What happened here? Bucket count. Oh, right. We cannot start with bucket count 0, so let's initialize this to 1. Okay. So this is 2 lines. We have a hash and a bucket count row. We're going from bucket count. Right. Let's leave this at 0. PTR count is count. Here, I think we need also to set the bucket count. That should have been set, meaning our make data as a bug. Bucket count, let's set Was bucket count 0 here? Okay, let's run it again and inspect the arguments. Right, this is not good. It should not be 0. Bucket count here. Let's put a breakpoint here and run it again. Right, bucket count is 1. That looks correct. We enter here. Count is still 1. Oh, now it's 0. Why is it now 0? Because count divided by 2. There's something wrong with our size computation. So the first insertion is fine, but the second insertion fails. Right. We should not divide this here. Only divide the bucket count. Oh wait. Also, we need to multiply. That was bad. We need to multiply it here. The division is fine. We need to multiply it. We want to grow it in the end. We don't want to make it smaller. Which also means that our table will always only grow. But this is fine. We can later add some improvement to allow to resize it down. But for now, that should be fine. 3 breakpoints and return. Still fail. Okay. Let's see. The one reference, we have 2 buckets and 3 entries. That looks correct. Right. So let's see how our get failed. We are here in get, we find entry, and find entry somehow failed. So F9, F5. So we get our hash. We get our index, so it should be in the first bucket. If hash is it the same? The next is fine. Key. Oh, our key is not initialized. That is a bug. Entry. Created the entry here, and we gave it key. Don't have a key from the key, and we are given a value that should. The P is correct. The party isn't. Just the breakpoint here, right? So entry. I didn't initialize both. That they were not capitalized. Initialized it with itself. Should have thrown us a warning. Would appreciate a warning here. And return. It worked. Got our number 2 retrieved from our table. And such a table, if it behaves correctly, usually gives you a very good performance. If dash function as mentioned fails and you just add of the values to the same bucket, then the lookup is extremely slow because then it needs to check every key and go through the whole table. That takes a long time. Right, we could of course now add some additional functionality like removing a key, for example. But before we do that, if we do that at all, are there any questions? No questions, okay. Then we could add some code to shrink the thing. Here maybe. Or when we said when removing, that's a good place to shrink. So let's add a remove. Willing move cons reference. Okay, reference key. Okay. And again, this is not ideal because it will either just remove one occurrence or the first occurrence or all occurrences. We cannot target the situation where we have multiple entries. So maybe before we do that, we'll make here make this a boolean and check if we have this key, then we just return false. If this, then just indicate an error that it couldn't be inserted because the key already exists. And true if we went through the insertion. And if we then want to enhance this, we can click about return result. So now we will search for it. We can copy that and that. And we can actually use an internal function, move entry, which just takes the entry and removes it. Yes, simply enough. So here insert value, find entry, but remove entry, s entry, asterisk p entry. Right. Good. So that's mapped. No, it wasn't. It was not because we would want to know what is pointing to this entry. Okay, let's not have an internal remove function. Let's just do it on foot. Or we could change this to return a pointer to a pointer. It would be better. So let's go. So as w pointer, return null, return reference on entry, because now we can modify whatever was pointing on. And then there where we are using it here, and then we need to asterisks Nice. And then if entry, no. Yeah, okay, this is fine. Remove get here too as well, but here we need to reference the outer one and then get the value, right? And here we technically it should be pp entry, pointer entry. This is important because if you not call it in the right ways, then it's easy to make a mistake. Okay. Here at pp entry, so we know we already have found it. We'll make a copy and this. Import is equals reference this one. Okay. Then p entry. Oops. P entry is equals p entry next. Next, yes, it doesn't want that. We need to. We could use alt as well, but let's keep this one. So this format it's unlinked. Then we can dispose of it. So we can build the destructor, call the destructor, and now reorg, reorg, yes, good. And point account must be reduced. So m atm count minus, and now we can make add some code to reduce the size of so if count divided by 2 is less than this, then here we just divide it by 2. And this must be less. This case that this is larger 0 cannot be because nothing can be less than 0 if we have only positive values. So this goes, this we don't need to check. But we probably don't want this to become 0. So if this is 0, then we set it to 1. So if this becomes 0, then this is just set to 1. Although this means that it already was 2 before. So in this case, if this is, we'll make it better. If this is not 0, then we do the resize, else we don't do anything because we don't want to do unnecessary things. Okay. So let's see if we now remove 222. We should get okay, we get an error first. Right, 2 p's here and there, and so I think. It is not. Just next, okay. Should have called it P next. Okay, that didn't work out unexpected. Robotic branch. We have decreased details. Did we run into the resize situation? This one didn't do what we want. Mm, mm, mm. Oh no, we broke something independent. Let's see what we broke. Um, hmm, it should be correct. Index is wrong. Index is not a big extension. Oops. Not a big broken make index. Bucket count is 0. Um, we fixed it already. Uh, we had this bug before. Hmm, no. Yes, so if this or then ptr bucket count is 0, then we then find doesn't find, shouldn't find. Okay, remove failed because we still got the value. Let's see why. Um, okay, we moved in the find 2 to 2. That is strange. No, that is still that. It's fine. We're just missing negation. Okay. Mm, okay, so our remove is not behaving as it should. Right, so we have the entry. So that is, we set it to the next. Um, okay, we decrease the count. Um, there was one negation too much. Okay, stay with happy. I said it now hitting the resize move entry. Um, and obviously somehow our remove entry is broken. So I want to move broken. Let's quickly comment this shrinking out just a second to see if then everything will work. Somehow it's not correct. Um, entry. Get an entry in a given bucket at index. So, it's the reference as well. We cannot do the reference. Okay, that complicates things. PP entry reference scan entry is not null. Scan entry No, this is not good at all. Because it should be non-destructive, and if we make it offense, it will be destructive. Mhm, mhm. Okay, it is not easily fixable. We will just revert our previous change and then make a dedicated delete function which does not use find entry. It complicates things too much. Um, if you are find, let's just do it. So we need hash, we need index, that is for sure. This probably will be fine. Yeah, once we fix this. Yes, okay. Enter, yes, address entry, WP equals reference and let's go PTR packets from index. Right. Type cover asterisk pp entry gleich an. Now we check for a match. If hash matches and matches, then we do something in between true. And if we, no, we don't have return true, we just break. So we will here return this as a test that we found in it. Maybe we'll see. Because we found it and we can break and break. We need to get rid of it. So I already have copied something before. Entry, entry, or bucket. We owned mptr, mptr, yeah, count minus means. Thus we would need to add this make exclusive to this one as well, obviously. This means that this exclusive make data zero, okay, then this needs to this false. And this, if we set entry to next, it still might be null, so this is not a good check. So let's say Good. Let's run. Okay. Asterisk. Okay. No. It's somehow I forget something. We are somehow running. We're not advancing the loop. We are not advancing the loop. So if it is not a match, then entry is equals if entry of entry is equals reference. Climate SSP entry. TP entry. Next. Okay. It's working. We removed the element successfully. And we are in time, out of time. So I will upload those two projects to Moodle. And if you have any questions, you can always contact me by email. There's something I wanted to mention. Someone had a question about the final project. Let's see if I can find it. Right. So there were a few questions. So one was, of course, how this casting should work. So what should work and what should not work. So let's quickly step through it. So we have a variant which you initialize with a string and then want to compare it or do something with it as a integer value. It should be able to cast from an internal string to just an integer if it's a numeric value inside. If it's like ABC or garbage, then just return 0. And if you have something that's a number, you should be able to cast it to a SCD string, but not to a C string, because a C string would require you somehow internally to hold the string, which we don't want, but we can return it to a SCD string, which will then hold an own copy. Alternatively, you can, instead of a casting operator here, since we explicitly create a new object, make like a toString function. And one last thing, which is also worth mentioning, you are prone probably to create a lot of very repetitive code, since you need to have a lot of things for every sort of variant. So like int 8, int 16, int 52, int 64, they're the same for uints, and float, double, string, white string, byte array, so it's a lot. And I came up with a small template and a demonstration. So what we're doing here is we are creating an own private constructor, which takes the type, the pointer, the data, the size of the data, and you can add some extra size. In this way, you can have all your constructors being one-liners, which just invoke this internal constructor. And for your cast operators, you can do it the same way. You can have like a generic template that returns you something of a given type, as shown here. And then you just provide the type, the return type for the thing to know, and then your own internal type identifier from your type variable. This is, of course, just a skeleton code, so it's not tested for working, just a suggestion how things can be done to save and don't create redundant code. So here you see the template function, which is quite simple. It uses this test and throw type and test and throw size, so that it tests whether there is enough size. So if, for example, you have just 8 bytes and you want an int32, then it's sorry, 8 bits and you want an int32, then it's always fine. You just pad the top with zeros or ones. But which is also mentioned here in the comment that if it's signed and not unsigned, then you need to check with what you will be padding it, which is not included here. That will do. And if you have like 32 bits and only want a byte, then you're checking whether the upper bits are actually set, because if they're not, then you can convert it and you won't have data loss. If they are set to something other than all ones or all zeros, then you will lose some data, in which case you should throw an exception if the exception throwing is enabled. I will maybe upload this to Moodle as well. I think maybe not as a file, but I think that there are some types where you can just upload text so that you all can take a look on it. Yeah, and we are over time, so that's it. We will see each other next week for the last time during the lecture. In the next semester, there is a part 2, which won't be that low level. So there we will be taking a look on a UI framework that allows us to create graphical interfaces and more interesting operating system mechanisms like threads, sockets, and so on and so on. Serial ports maybe. So it's highly recommended to also visit part 2 next semester. And in addition to the part 2, there is also a exercise, which is at the same day, just in the morning. It only takes 1.5 years. Code publicly during the exercises. I prepare something, and then you can implement things. We could implement a really nice useful helper functions, or we could implement a own big number class, so big integer, something that we can use for encryption, and so on. So this is also recommended. Yeah, I will mention this next time again, but my experience from previous semesters and years was that this information kind of was not so apparent as I assumed. So now I'm mentioning explicitly. So have a nice weekend and see you next week. Bye bye.